Hi, I'm Isabella Zaniletti, and I'm a biostatistician at Mayo Clinic. In this video, we will learn about myths and realities surrounding p-value and power in statistics. Orthopedic studies often involve the statistical estimation of surgical outcomes. The results of the statistical analysis are typically reported using p-values. P-values are one of the most misunderstood and misused statistical concepts. P-value measures the incompatibility of the study data with the null hypothesis. Assuming that there is no true difference between two comparison groups, the smaller the p-value, the less compatible the data are with the hypothesis of no difference. On the other hand, a large p-value would suggest that the study data are compatible with the null hypothesis of no difference. Consider this scenario. In a cohort of 1,000 total knee arthroplasty patients, investigators want to compare KOOS scores between male and female patients. The null hypothesis is that there is no difference in the mean pre-op to 6 months post-op change in KOOS scores between males and females. The observed mean change in KOOS scores is 12 points in men and 10 points in women, with a p-value of 0.02. A p-value of 0.02 suggests that if chance alone was creating the inconsistency between the data and the null hypothesis, the inconsistency would be as large as observed or larger, 2% of the time. In other words, if the same analysis is repeated 100 times on separate data sets, a difference of this size or larger will be observed in 2 of the 100 data sets. There are several misconceptions surrounding the use and interpretation of p-value, so a thorough evaluation of the contest is fundamental. It is good practice, for instance, to accompany the p-value with confidence intervals to provide details on the size of the estimated effect that might be missed otherwise. Here are 6 different scenarios of 95% confidence intervals for the difference between females and males with respect to pre-op to 6 months post-op change in KOOS scores. The width of confidence intervals depends on the sample size and variability in the data. Larger studies tend to have narrower confidence intervals than smaller studies. Even though the estimated effect size is the same in scenario C, E, and F, the smaller confidence intervals in scenario C indicates a much more precise estimate of the group difference that is typically achieved in larger studies. In scenario C, we would have a significant p-value if we test for a minimal clinically important difference between groups. But in scenario E, the p-value will be significant if we test for a difference greater than 0, but not for a difference greater than the minimal clinically important difference. In scenario F, we would not detect any difference at all, since the confidence interval includes 0. So how many patients do I need, and how do I power my study to make sure I detect a difference between two groups when the difference truly exists? The answer to these questions depends on 3 characteristics of the study: type 1 error, type 2 error, and the magnitude of the difference in outcomes between the comparison groups. This is also called the effect size. Let's talk about type 1 error. Type 1 error is the error of rejecting the null hypothesis when it is true. Type 1 error would lead to the conclusion that a difference between groups exists when in reality there is no difference. To control for the likelihood of this error, the level of significance of the test is set prior to beginning the data analysis. The probability of a type 1 error, or alpha, is typically set to 0.05 or 5%. The second type of error in hypothesis testing is type 2 error, which is defined as failing to reject the null hypothesis when in fact it is false. As the likelihood of this error, beta, increases, the statistical power decreases, and vice versa. There is a trade-off between type 1 and type 2 error. The more the risk of one type of error decreases, the more the risk of the other error increases. For instance, if there are many similar hip prostheses on the market that function well, and a new prosthesis is very expensive, you may want to minimize the risk of claiming the new prosthesis is better when it is not really different from the others, even at the expense of an increased chance of missing a superior prosthesis. And now on the effect size. Effect size is the difference in the group means relative to the variability in the outcome if such outcome is continuous. If the outcome is categorical, effect size is expressed as proportion or odd ratios. In time to event analysis, the effect size is the hazard ratio. In this figure, we can appreciate how type 1, type 2 error, and effect size are related. A study is conducted to evaluate femoral stem subsidence. The cohort includes elderly patients who underwent primary cementless total hip arthroplasty. The two curves represent the distribution of the difference in mean stem subsidence under the null and alternative hypothesis. If the mean subsidence in males is truly greater than the females by 2 millimeters, and there is adequate power to detect the difference of this size, the null hypothesis is rejected. An increasing type 1 error causes a decrease in type 2 error and a consequent increase in power. Power also increases if the difference between groups to be detected is larger. In conclusion, p-value does not measure the probability that the null hypothesis is true, nor the probability that the data were produced by random chance alone, nor the magnitude of the treatment effect. P-value is a measure of the incompatibility of the study data with the null hypothesis. Conclusions should not be based only on whether the p-value is smaller than the predetermined level of significance. We recommend adding confidence intervals to provide useful information on the range of the estimate.